the properties of the system we need to verify here. The first property is called linearity property. Already we are done with this property, linearity property. Okay, so done everyone?
Yes, sir.
Okay, so next let us go for the next property, which is called as the stability property here. Okay, so let us take the B, which is called as the stability property. Okay, so take stability property. Stability property. Okay, so stability is the thing, but we need to find out whether the system is stable or not. We need to find out here. So let us take let us consider the signal, given signal y of t is equal to e to the power of x of t. Okay, so let us consider the magnitude. Y of t is, when you consider magnitude, it will become, so magnitude of e to the power of x of t, it will become here magnitude of e to the power of x of t. So let us split the magnitude for the individual terms. So e to the power of the magnitude of x of t, the magnitude of x of t. Okay, so when you consider the magnitude of x of t, so obviously the system will be not a stable system will be there. Okay, so since okay, so we are considering the magnitude of x of t, we can say if the x of t is a finite value, then the x e to the power of x of t will be the finite value will be there here. So you can say, so the magnitude of x of t, if the magnitude of x of t is less than mx, is less than or equal to mx, is less than infinity. Okay, so you can say that is if the input is bounded, if the input is bounded, means if the input is a finite quantity, then y of t is also bounded here. So just I'll write here, then y of t, the magnitude of y of t is less than my, is less than infinity. So it will be the stable system here. So if the input is a finite quantity, for example, if x of t is equal to something 10, 20 or 100 or something will be there. So then this will be the finite quantity will be there here. Otherwise, it will be not a stable system here. Okay, so we are putting the condition here. If x of t is bounded, then y of t will be also the bounded quantity will be there. Okay, so y of t will also be the finite quantity will be there. So it is called as a stability. So done. Okay, so we are done with the stability. Now let us go for the next property, which is called as the memoryless or memory. So the property number, it's a third property. So it's a memory. So memory or the memoryless. So the given system is nothing but y of t is equal to the e to the power of x of t. So if you want to find out the memory, let us substitute t is equal to 0. So that y of 0 will become e to the power of x of 0. Okay, so it depends on present value only. Let us substitute t is equal to something called 1. So y of 1 will be depends on the e to the power of x of 1. We can see the present input depends on the present output only here. The present output depends on the present input only. So the given system is a memoryless system here. We can say the present. Okay, the present. What we can say is the present output depends only on the present input. Therefore, the system is a memoryless system here. The system is a memoryless system. The system is a memoryless system. The system is a memoryless system. Okay. Then the system is a memoryless system. Okay, now let us verify for the causality. Let us verify for the causality property. So causality is nothing but the output does not depend on the past values or future values of the input. That one you're going to call it as a causality. So since we are observe here at t is equal to 0, the present output depends on the present input only. It does not depend on the future values of the input here. Okay, so you can say the present output does not depends on the present output does not depends on the depends on the future values of the input, future values of the input, future values of the input. So therefore the system is causal system here. It is a causal, it is not an anti, it is a non-causal, it is not an non-causal system, it's a causal system. So causal system is nothing but the present output does not depend on the future values of the input here. That one you're going to call it as the causal system, you're going to call here, causal system. Okay, done, right? So done. So next one is nothing but the time invariance property. Time invariance. Okay. So the time invariance, what you are going to do, you are going to given the system y of t is equal to e to the power of x of t. It has been given here, e to the power of x of t. Let us replace x of t by the x of t minus t naught here. X of t minus t naught. Let us do replace here, so that it has become y of t is equal to the e to the power of x of t minus t naught. You'll get here t minus t naught. Okay. Now call this as equation number 1 here. So similarly, let us replace t by the t minus t naught. So let us call this one as y1 of t. So let us replace t by t minus t naught in the y of t. In y of t, this is the y of t. So it has become y of t minus t naught is equal to the e to the power of x of t minus t naught here. So compare the RHS part of the equation 1 and 2. Okay. So if you compare this one, comparing, okay, so equation 1 and 2. So if you compare the equation 1 and 2, so therefore the given system is time invariant system here. Given system is time invariant system. Okay, so the given system is a time invariant system here. Okay. Any doubts? I think you got some idea how to find out the properties of the system. So right. Done. So I think everyone has taken.
Yes, sir.
Yeah. So let us go for the next problem. So take the problem number 9. Y of t is equal to x of t by 2. Y of t is equal to x of t by 2. Then, so this is the system. In this system, we are going to give the verify the property which is called as the memory. Let us verify, and even the causality. Let us take bit interest here. Other than the remaining properties, will remain same here. Okay, so let us find out the first one, which is called as the linearity property. So linearity property. Okay, so linearity property. Let us do verify here. So what shall we do is, so the given system is y of t is equal to the x of t by 2. X of t by 2. Let us substitute x of t is equal to the a1 into x1 of t plus a2 into x2 of t. So what the given system is going to do, if you are going to use the x of t as the input, it is going to scale the time by the 1 by 2. It is going to scale here. Okay, so that is going to be scaled by the system here. So let us, if you are going to give that as the input here, so y of t is equal to the, so it will become a1 into x1 of t by 2 plus a2 into x of t by 2 will get here. So call this as equation number 1 here. So the input time interval will be scaled down by the 1 by 2 here. Got it? So similarly, let us give the input as the single input. Let us give here. So that is h of a1 into x1 of t. a1 into x1 of t. Let us give that as the input here. So this has become a1 into x1 of t by 2 will get here. x1 of t by 2. Done. So similarly, y2 of t is equal to the h of a2 into x2 of t. Let us give here. So the output will become a2 into x2 of t by 2 will get here. So let us combine this one. y3 of t is equal to the a1 into x1 of t by 2 plus a2 into x2 of t by 2. So call this as equation number 2. Compare equation 1 and 2. The given system is a linear system here. Compare equation 1 and 2. Therefore, it is a linear system here. So what are the output you'll get here? So underline that one here. Then next one is causal. So obviously this will be the causal system will be there. So causality. Okay. For verifying the causality, let us consider a system y of t is equal to x of t by 2. Okay. So consider the magnitude of that one. So whenever you consider the magnitude, it will become okay. So less than or equal, it will become here. So you can say if x of t, okay, if x of t, the magnitude of x of t is less than or equal to the finite quantity is less than the infinity for all values of the t. So if x of t is a finite quantity for all the values of t, then obviously y of t is also the magnitude of y of t is also the less than or equal to my is less than infinity. Okay, so therefore the system is a stable system here. It is a stable system. It is a stable system. Okay. Then, so this is a stable system we'll get here. Done everyone, right? So next what I'm going to do, which are the problem will be there. I'm going to take the special cases. Remaining properties I'll leave for the you so that you can do the remaining properties. Okay. So that I can save the time and I can I can solve the many variety of problems which is of particular properties will be there. I'll take the top interest here. So remaining properties you can do it by yourself here. Okay. So next one is called as memoryless or the memory. So memoryless or memory you can take here. Anyone is okay. Property name. Okay. So fine. So now what we'll be doing, the given system is nothing but y of t is equal to the x of t by 2. Okay, if I substitute t is equal to 0, so y of 0 will become x of 0. Okay, so for the 0, it is okay. Let us take the another time interval t is equal to 1. So y of 1 is equal to the x of 1 by 2. So x of 1 by 2 is nothing but it's a past input here. Past input, correct now? So similarly, if I substitute t is equal to 2, so y of 2 is nothing but the x of 1. So this is also nothing but the past input. Past input. Okay, so that it has memory or it is a memoryless system. So the present output depends on the past input. No, the present output depends on the past input here. So that it has memory or memoryless.
Memory, sir.
Yeah, it has memory. Okay, so very good. So you can take since the present output, since the present output depends on the depends on the past values of the input, therefore given system has memory. The given system has memory. Okay, so whichever the topic is there, you can just underline here. The next property is called as a causality property. Okay. Done, right? Okay, now next let us go for the causality property. So what's the causality says is, so the present output does not depend on the future values of the input here. It should not depend on the future values of the input here. So x of t by 2 it is given. Okay, so when I substitute y of, let us take t is equal to the -1, I'll take here. So in order to verify the causality, I'll take the negative values I'm going to take here. So y of -1 will become equal to the, so x of -1 by 2. Y of -1 is equal to x of -1 by 2. Okay. So it means that, so it depends on the past values of the input here. Okay. So that is, sorry, it is depends on the future values of the input here. So we can say it is a non-causal system, we can say it here. when I substitute t is equal to -1, it depends on the x of -1/2, it depends here. Okay, so this is a present value. This is nothing but the some future value it is we are going to consider here, because in the negative time index we are going to come here now. So -1/2 -1. So this is present, means it depends on the future values here, like this here. Okay, so we can say, so since the present output depends on the future values of the input here, we can say it's a non-causal system here. Since the present output depends on the future values, depends on the future value of the input, future value of the input. Okay, it is a non-causal system here. The given system is a non-causal system. Okay, so got it now. How to find out the causality and the memory loss is like that. You can substitute the positive values and you can substitute the negative values for finding the causality, and you can find out that one here. So it depends on the nearby values like -1/2, something like that here. So we can say it's a non-causal system here. Okay, so next one is nothing but the time invariance property or the time invariant systems. Time invariant systems. Okay. So let us verify the time invariance. So it is given y of t is equal to the x of t/2. X of t/2 has been given here. So what shall we do? We shall replace the t by the t-2. Let us do replace here. Okay, so replace t by the t minus t0. So let us say y1 of t is equal to the x of t minus t0 divided by 2. T minus t0 divided by 2 will get here. Done. Done now. So we are going to replace the t by t minus t0 here. So it has become t minus t0 by 2 will get here. So similarly in y of t, so replace t by t minus t0 here. So it has become y of t minus t0 is equal to the x of t minus t0 divided by 2. T minus t0 divided by 2. Okay. Done. Now compare this expression. So comparing. Okay, so the given system is a, so since both are same here, the given system is a time invariant system here. The given system is time invariant system. It is a time invariant system here. Done. Okay. Okay, I'll go for the next problem. Is it okay, right? No doubts in this problem. So I'll go for the next problem. So take the next problem. So y of t is equal to the d by dt of x of t. So the differentiation of the input. Okay. So we're going to give the input. The output will be the differentiation of the input we'll get here. Okay. So let us verify the linearity property. So linearity property. Let us verify the first one here. So what you are going to do is you are going to substitute the so it is the system. Let us write the given system here. So d by dt of x of t. Okay, let us substitute x of t is equal to the a1 into x1 of t plus a2 into x2 of t. Okay, let us substitute here so that y of t will become, so d by dt of a1 into x1 of t plus a2 into x2 of t. So this has become, so since it's addition, so differentiation is going to follow the linearity property. So it is x1 of t, differentiation of x1 of t plus the differentiation of the x2 of t will get here. X2 of t will get here. So call this as equation number 1. Okay. So we are going to replace the x of t by the a1 into x1 of t plus a2 into x2 of t. We are going to do replace here. So next, what shall we do is let us give the individual inputs as the individual inputs. Let us give it here. Okay. So let us say y1 of t is equal to the a1 into x1 of t. Let us give as the input here. A1 into x1 of t. Okay. So that I am going to give. So it will become a1 into d by dt of x1 of t. So similarly, y2 of t is equal to h of a2 into x2 of t. Let us give that as an input here. So it has become a2 into d by dt of x2 of t. Add these two things. So y3 of t is equal to the, so a1 into d x1 of t divided by dt, a2 into d by dt of x2 of t. So compare equation 1 and 2. Call this is equation number 2 here. So comparing, okay, comparing equation 1 and 2. So it is a linear system here. Since both are one and the same, the system is a linear system here. Excuse me. Then next, let us verify for the causality. I'm going to keep pending for this one. So because the causality, some confusion is there for me. So that's why I'm going to keep this one as a pending for the causality. So I'm going to take the remaining properties I'll take here. So sorry, stability I'm taking here. Stability. So I'm having a bit confusion. So I'll take the stability property later. Okay. So I'll take for the next one is called as a memory. So all the differentiators will be having the memory because you have seen the capacitor in the last semester. You have seen in the network theory. So it has memory. So you can take the differentiator is having the memory. So this is an example of the differentiator here. Differentiator is having the memory. So therefore, the given system is as memory. The given system has memory. Done. Okay, so the given system has memory. So because all the differentiators will be having the memory, so the capacitor is example of the differentiator because it is going to store the energy from the past time infinity to the present value. So it has the memory will be there here. Okay, and when you come to the causality, the differentiator is okay. So it depends on the future values also, because why you know say no. So because t is equal to minus infinity, if I take the energy stored in the capacitor, that is we know that v of t is equal to the, so the voltage across the capacitor is 1 by c integral from minus infinity up to the t. So I of tau into d tau, no, I of tau into d tau. This is the voltage across the capacitor you're going to find out here. So from minus infinity up to 0, this will be considered as the future values you're going to consider here. Future values here. So that's why it is said to be the non-causal system here. Okay, it is said to be the non-causal system. You're going to say it here. So you can take. Okay, so for the causality, so you can take. So since the present output, so causality, since the present output depends on the future values of the input. Future values of the input. Therefore, it is a non-causal system. It is a non-causal system. The given system is a non-causal system here. Okay, so other one is the time invariance. Time invariance, let us check out here. Okay, so done. Any doubts in any of the properties? If you have any doubts, you can ask me. Okay, so the differential is d divided by dx of t. Okay, so time invariance, you can verify the property. So replace t by t minus t naught. So replace the t by the t minus t naught here. So t minus t naught. So y of t will become, let us say y1 of t, it is equal to dx of t minus t naught divided by dt. Dx of t minus t naught divided by dt. So similarly, replace. Similarly, let us replace. Similarly, let us replace t by the t minus t naught in y of t. Okay, so it has become y of t minus t naught is equal to dx of t minus t naught divided by dt. Let us compare. This is equation number 3 and 4. So comparing 3 and 4. Okay, so the given system is it's a time invariant system here. Time invariant system here. The given system is a time invariant system. Right. So stability, let us leave some space here. I'll do stability in the next class. I'll do that one. Okay. So done. Okay. So we'll go for the next problem. Then so far many problems here done. Okay. Let us go for the next problem here. Okay. So I'll take the next problem. Take problem number 11. So y of t is equal to the cos x of t. Y of t is equal to the cos x of t. Okay. Done. Okay. So let us verify. The first one is called as a linearity property. So linearity property. So linearity, we are going to replace the x of t by the x1 of t plus x2 of t. We are going to replace here. Okay. So let x of t are going to substitute as the a1 into x1 of t plus a2 into x2 of t. a1 into x1 of t plus x2 a2 into x2 of t. Let us do substitute here. So it has become y of t is equal to cos of a1 into x1 of t plus a2 into x2 of t. Okay, so this is in the formula of cos of a plus b. So if you apply the cos of a plus b, it is cos a cos b minus sin a sin b will get here. So we're not going to expand that one here. We are going to call this one just as equation 1. We are going to call here equation 1. We are going to call this one. So just we are going to keep like that only. So right. Done. So now let us take the individual input here. Let us take the individual input here. So let y1 of t is equal to the, so the system operator is nothing but h. So h of a1 into x1 of t. So the output will be, so a1 into, it will become a1 in cos of a1 into x1 of t will get here. Okay, so we can't say cos of a into x is nothing but, we can't say it as a into cos of x, we can't say. So we should keep like that only. So similarly, y2 of t is nothing but, so h of a2 into x2 of t, a2 into x2 of t. So this has become cos of a2 into x2 of t, cos of a2 into x2 of t. Let us add these two here. So y3 of t is equal to the, so cos of a1 into x1 of t plus cos a2 into x2 of t. So call this as equation number 2. So comparing equation 1 and 2, comparing equation 1 and 2, we can say it is a non-linear system because these two are not equal here. So we can say it's a non-linear system here. The given system is a non-linear system. Then okay, any doubts? So take the next property, which is called as the, so first one is linearity property, next one is called as stability. Stability. Let us take y of t is equal to, so cos y of t is equal to the cos x1 of t, cos x1 of t. So if you're going to consider the magnitude of this one, the magnitude of y of t is nothing but, so the magnitude of cos of x of t, cos of x of t. Okay, so you know what is the maximum value for the cos signal? If you're going to consider the magnitude, what is the maximum value it can take here? Cos signal. What is the maximum value for the cos signal it can take? So if I'm going to plot the cos signal here, so here there is no scaling factor here, so it is going to be taken like this here. When I say cos 0, the maximum value will be the 1 here. So cos minus pi, when I say it here, it will be equal to the minus 1 will be there here. Okay, so the maximum value will be the plus 1 and the minimum value will be the minus 1 is there. So since we are going to take the magnitude of that one, so cos of any signal is nothing but it is going to lie either between the plus 1 or the minus 1, it is going to lie here. So this, the magnitude of this one will be equal to the 1 will be there. Okay, so the magnitude of this one will be equal to the 1 will be there. So we can say that the magnitude of, okay, so y of t, okay, so the magnitude of cos of x of t, so this one will be less than, okay, this value will be equal to the 1, which is less than infinity will be there. So the given system is it's a stable system here. So got it now? The maximum value of the cos function will be 1 only, which is less than 1. So therefore y of t is a stable system here. Y of t is a stable system here. Then so the maximum value of cos will be equal to the plus or minus 1 will be there. So the given system is a stable system will get here. Done, right? Any doubts in this one? Okay, so similarly, let us find out the time invariance here. Let us find out the time invariance. So if you have any doubts, you can ask me. Okay, so let us go for finding the time invariance property. Time invariance. Okay, so let us find out the time invariance here. Check this one. Time invariance. It's a time invariant. So what we should do is, so we should replace the x of t by the x of t minus t naught here. So replace x of t by the x of t minus t naught here. So replace t by the x of t minus t naught here. So what you'll get is, so it has become y of t is equal to the, okay, so cos of, it has become cos of x of t minus t naught will get here, cos of x of t minus t naught. Okay, so let us say this is nothing but y1 of t. Call this as equation number something to 3 here. Already we have taken 2. Okay, call this as equation number 3 here. Okay, so now let us replace t by the t minus t naught here. Let us replace t by t minus t naught in the y of t. So replace t by t minus t naught. Replace t by t minus t naught in y of t. So it has become y of t minus t naught is equal to cos of, wherever t is there, you can do replace with the t minus t naught here. Okay, so call this as equation number 4 here. So compare equation 3 and 4. Compare 3 and 4. We can say, and therefore, the given system is linear system here. Is a linear system. Sorry, it's a time invariant system here, not linear. It's a time invariant. Time invariant system here. Done. Any doubts? Okay, so let us go for finding the memory. Let us go for finding the memory here. So y of t is equal to x of cos x of t. So y of t is equal to cos of x of t. Y of t is equal to cos of x of t. So if I substitute t is equal to 0, so y of 0 will become cos of x of 0. Okay, similarly t is equal to 1. So y of 1 is equal to cos of x of 1. Okay, so therefore the present output depends on the present input only. So therefore the present output depends on present input only. Therefore the given system is a it's a memoryless system here. You don't have memory, so it is a memoryless system. Okay. Similarly, I can say the causality also, you can say it's a causal system here because it does not depend on the future values of the input here. Okay, causality also similarly we can say it here. So right, check for the causality. So you can say that the given system is a causal system here. Done. Done with the causality, right? So you can write, so since the present output does not depend on the future values of the input, the given system is a causal system. The given system is a causal system. Since the present output does not depend on the future values of the input, the given system is a causal system here. Okay, so done. Any doubts with this one? Take next one. Any doubts with this problem? No doubts, no? Okay, so take the next problem. So take the problem number 12. So in the next class, I will take some more problems I will take here. And I'm going to wind up this one. I'll go for the next very important topic, which is called as the convolution theorem here. Okay, So convolution is we have plenty of problems are there. So it will take much more time to solve this one here. Okay, so delta of n minus 2k. So take y of n is equal to x of n, summation k is equal to minus infinity to plus infinity delta of n minus 2k. Delta of n minus 2k. Okay. Done. Okay, so let us verify the linearity property. What it is going to do, it is going to take the product of x of n with the delta of n minus 2k here. So when n is equal to 0, so delta of 0 minus 2k it will become, so the product will not exist here. So like that here, let us do verify this property. So first one, let us take the linearity property. So linearity property. Okay, so take the linearity property of this one. Okay, first one is the linearity property. Let us do verify. So what we need to do is let us substitute x of n is equal to the, so let x of n is equal to a1 into x1 of n plus a2 into x2 of n. Let us do substitute here. So y of n is equal to, so a1 into x1 of n plus a2 into x2 of n. So that one is multiplied by the summation k is equal to minus infinity plus infinity delta of n minus 2k. So now I'm going to multiply the individual terms. It has become, so a1 into x1 of n summation k is equal to minus infinity plus infinity delta of n minus 2k plus a2 into x2 of n into summation k is equal to minus infinity plus infinity delta of n minus 2k will get here. So call this as equation number 1. Call this as equation number 1 here. Okay, so similarly, let us give the individual input. Let us give and let us see, verify what is the output you are going to get here. So h of, okay, so I will give that as the input here. So h of a1 into x1 of n. So if you are going to give that as the input here, so it has become a1 into x1 of n. So multiply by summation k is equal to minus infinity plus infinity delta of n minus 2k will get here. So similarly give h of a2 into x2 of n. So this has become a2 into x2 of n into summation k is equal to minus infinity plus infinity delta of n minus 2k will get here. Delta of n minus 2k. Okay, done. So now add these two quantities. Let us say this is nothing but y1 of n. Let us say this is nothing but y2 of n here. Okay, so add these two quantities. So it has become y of n is equal to, so a1 into x1 of n into summation k is equal to minus infinity plus infinity delta of n minus 2k plus a2 into x2 of n summation k is equal to minus infinity plus infinity delta of n minus 2k. So by comparing this one, I'll call this as the equation y3 of n here. So compare equation 1 and 2. Compare equation 1 and 2 here. If you're going to compare, the given system is a linear system here. It is a linear system. Done, right? So like this, we need to substitute a1 into x1 of n and all those things here, and we'll get that one. Done, right? So next, two simple properties I'll take here. So memory. So since at n is equal to 0, it depends on n is equal to 0 only. Okay, so we can say it is a memoryless system. We can say it here. Okay, so it is a memoryless here. So I'll take the next property as memory. So memory. So y of n is nothing but x of n summation k is equal to minus infinity plus infinity delta of n minus 2k. Okay, since you can see here also n, here also n here. So both the ways n is there here, we can say it's a memoryless system here. For example, here n minus n naught is there, or n by 2 is there, something here. So don't consider the rest of the things here. Just you consider about these things here. Okay, so since at n is equal to 0, so y of 0 depends on the input x of 0 only. Multiply with the scale by the some other factor, something called delta of n minus 2k. Okay, or even if you want, you can say n is equal to 1 here. Okay, n is equal to 1 this one here. So we can say the system is a memoryless system here. It's a memoryless system here. So since the present output depends on the present input only, it's a memoryless system here, right? And also causal, it is also it's a non-causal system here. Why? Because the present output depends on the n is equal to 1 only. So if I say 1 is equal to 1 here, also 1 here. So it's you can say it as a causal system. You can say it here. Okay. So it has it is a memoryless here, and it is a causal system here. Let us take the next property, which is called as a causality. Causality. So since the present output, does not depends on the future values of the input here, depends on the future values of the input, so it's a causal system here.